Hi, I'm Ed Kohler with Extreme Networks, and I'm here today to talk to you about the Internet of Things, or IoT. Now, most of us, when we think about IoT, we think about small devices like this nifty little video surveillance camera. We also might think about something a little bit more sophisticated, like this patient monitoring device. Pretty cool, very innovative. Also, we might think about something a little bit more fun, like this wearable badge. This is a badge from DEF CON, and it was used to track me, to allow me access to certain venues, and it also tracked my progress as I moved through the different workshops. All in all, it was a pretty fun experience and a pretty cool memento. But IoT is quite a bit larger than that. IoT is embedded throughout our physical environment. Obviously, in our metro area, in our roadways, in our waterways, our power grids, but also even out to agriculture and forestry. Now, these little devices are embedded in our physical environment. All in all, by themselves, they are not that intelligent. So, how do these small little devices build up an intelligent infrastructure or a smart community framework? That's what we're going to talk about here in this session. So the first thing we need to realize is all of these small little IoT devices are interconnected somehow with networks. Now, very seldom will you see power grids, waterways, forestry services, metro safety, all in one single network. Usually you will see separate networks and separate organizations. What we're going to talk about is something a bit more profound. So I'm not going to get into how the systems are broken out at the network level. We're going to kind of abstract the whole plane, and we will refer to it as cyberspace. And cyberspace is overlaid on top of physical space. Now, obviously, cyberspace is created by a series of network switches which are interconnected together. We will simply refer to that as Fabric Connect. But we also have to realize that a good amount of edge connectivity now is wireless, so we have to list out Wi-Fi as well. And another very important point that's going to be a major point to the discussion here today are the compute systems that are embedded into the cyberspace infrastructure. Now, all of these network switches and compute systems obviously exist in physical space. The network switches are embedded into our roadways, into our waterways. The compute systems reside in data centers that may either be within the actual physical environment or perhaps based in cloud services. We'll draw a couple clouds here to represent multi-cloud. But we're not going to stop there. There's an important level of consideration that goes above this, which is the key to our discussion here. So I'm just going to draw a dotted line. And then above that, I am going to refer to this as the metaspace. And meta being the Greek term for beyond, and it's very appropriate to this discussion. What goes on in the metaspace is purely software. It's purely logical. It is ethereal in many ways. It exists within the compute systems, obviously, and run code, but it's largely algorithmic in nature. Now, a lot of folks, when they hear about algorithms, they go, whoa, wait a minute, that's getting technical. And It can be. Algorithms can be complex, but really, for the level of conception that we require for this video, I can give you a few simple examples. Let's say you want to get up in the morning and you decide you want to make a Western omelet, which is an omelet with cheese, well, no, cheese, onions and peppers and maybe cheese. So you go into the fridge, you look, you say, okay, I have my eggs, but oh, I don't have any onions. So you say, okay, well, all right, well, we won't have our Western, which I really wanted, but we'll just make a cheese omelet. So you look further and you say, oh, I don't have any cheese. So now you say, okay, well, I have the eggs, I have some sausage, I'll chop the sausage up. I also have a little spinach, so I'll throw it all in and I'll make a scramble. And then you have your breakfast. And then afterwards, you decide that you need to go shopping. But really, in reality, what happened is you started with an algorithm. And that algorithm was your Western omelet. And then through intercourse with the environment, you got feedback that you could not run that algorithm successfully. So you reverted and created a second algorithm. And that second algorithm was the cheese omelet. And again, through iteration with the environment, the feedback was negative. The algorithm would not run. So what you did is you created a radical third algorithm. It was directly interacting with the environment and what you had in your fridge. And these are algorithms. Notice how different algorithms were created in reaction to input from the environment. Now, there's another example of an algorithm that I think is a bit more profound and case point to this example, although algorithms often are created on the fly in reaction to input. Now, everyone runs the same algorithm when we walk into a room. We come in, open the door, and we look around the room. And if we see someone we know, we will move forward and we will smile, we will shake their hand. And if we haven't seen them in a while and we're close, we may even embrace. That is a typical output to the input. Okay? The input was me walking into the room and seeing a friend. The output was the behavior, my handshake, my smile, my embrace, possibly. Now, let's take another scenario. Let's take the same room on a different occasion. And we open the door, and instead of finding someone we know, instead there's a very large, mean dog in that room. We would back out of the room immediately and we would slam the door. That is a drastically different output to a drastically different input. So we're going to stick along that theory, a singular algorithm that reacts differently and provides different output according to singular input. Although realize that the more profound aspect of dynamic creation of algorithms does indeed exist within the intelligent infrastructure, but we're not going to go too complex in that direction. So basically, in the algorithmic space, it's best to use some case point examples of how this works. Now realize that these algorithms do run in the compute systems and they provide input from the IoT environment. And with that, we can realize that the compute systems and the algorithmic exist within the cyberspace and environment and are more or less embedded into the network or fabric infrastructure. So when we look at this, let's use our first case point example, and that is green energy. Green energy is very laudable. It has gotten a lot of attention as of late. So we're going to take a focus in that. And basically, this is the use of renewable resources such as wind or solar in order to enhance our capacity for power generation. Now, we can slap in some solar panels and perhaps put up a few windmills, but it's really not quite as easy as that. A lot more complexity involved, and I'm going to give you a couple case point examples. One, the most familiar, is the recent event that happened this past winter in the southern US. You had major portions of the power grid that were taken out due to a massive ice storm and blizzard. And basically, most of the solar panels, if not all of them, were covered over with a glaze of ice and a good 4 or 5 inches of snow. And the windmills were either frozen or shut down to the ice, which meant that close to 2/3, maybe even more, of their power generating capacity was gone. They were really only left with a conventional hydroelectric or geothermal. So That is one lesson, but we don't need a drastic weather event to demonstrate this. I've been following this for quite some time. Several European countries have been moving more towards green energy and green energy. And what they found is once you get around 20% of the power generation capacity, you have the potential of injecting imbalance into the power grid. Many people don't realize, but the power grid is a living, dynamic entity that's based on power generation and demand, and that balance has to be maintained constantly. The reason for that is we don't have the storage resources and technology yet available to handle this green energy. And why is that? Well, we have to realize that while geothermal can run fairly consistently day after day without any impact from the environment, hydroelectric can do the same for the most part, unless it's an extreme drought situation. But that is not the case with solar and wind generation. These are variable, and in some cases, extremely so, depending on the region, the location, the time of year, and all of that needs to be taken into consideration and balance. So not only are we talking about balancing the systems themselves, the actual wind resource, our solar resource, and our conventional geothermal and hydroelectric, these obviously need to be interconnected and provide a feedback mechanism. But not only do we need to do that, we need to consider input and reaction with the environment given the variability of these green resources. So this all results in a series of algorithms that reside up in the algorithmic space to provide the ability to judge the state of the power grid as far as its balance is concerned. Now, how does this happen? Well, obviously, sensors provide information and feed up into the cyberspace environment. And we're going to just draw some upward arrows here, and those will be used as sensor input from the physical environment for the rest of the use case examples as well. Now, obviously, this information feeds up into the algorithmic space where numbers are crunched. And throughout the process, decisions may be made to actuate. We may decide to spin up or down some windmills. We can do the same with solar. We can do the same with hydroelectric capacity. And basically, that provides us an actuary capability back down in the environment to provide and maintain that balance. So now you can see that even though the sensors are relatively dumb, there's a cohesive intelligence that creates, because the sensors almost become equivalent to our senses. And our cognitive loops up ahead of us in our brain allow us to run algorithms. This is a very close analogy. So we get to the concept of a brain starting to develop here. So what we'll do is we'll just draw a little brain icon here. And we can see that through sensing the power grid and its associated balance, we can run intelligent algorithms against that. Now, there is another subsystem that is drastically or intimately related with the environment, and that is our waterways and water distribution. Here we can see that we have our waterways and water distribution. Directly related to power grid would be hydroelectric. So what we'll do is we'll put some sensors at the hydroelectric facility because we're going to assume those are there. But we also realize that there are sensors and intelligence embedded into the waterway that can give us feedback as far as the state of the waterway, its level, its flow, and these sensors are populated. And it also provides feedback for capacity for hydroelectric. Well, this is just a little symbolic type diagram showing us our water course. And then, of course, after the dam, we probably have some sensors upstream as well. And so now we have a representation of the physical waterway environment in cyberspace. And it allows us to judge the water level It allows us to feedback our power generating capability, and that resides or creates another set of algorithms up in the algorithmic space, which again may be on a separate network, but it's the same brain. And from that feedback, we have this implicit notion of availability of the hydroelectric resource to the power grid, and then also the ability to handle the resource for public water distribution, runoff, storage, reservoirs, things of that nature, all which are managed in a cohesive system framework. So now we start to get the notion that these IoT devices do have some visibility once they're married up into the algorithmic space through the capacity of cyberspace, which is the fabric network. So now let's consider our third example of a highly interactive feedback environment, and that's obviously forestry and agriculture. Now, I'm going to add in a couple other entities at this point, because it will enter into our talk, is that there is an advent of 5G in the use of these technologies and increasingly in smart city infrastructure. So we'll draw a little 5G tower. And then also we cannot forget our old friend, satellite, GIS, GPS, available to us. And you can see that now we're creating a significant arsenal of data acquiring and the ability for actuary commands back down. Now in forestry, it's largely monitoring. We monitor the state of the forest, we monitor growth, we perhaps monitor for pests, things of that nature. Very seldom, although that may change in the future, we very seldom actuate anything down into the forest. So it's usually just a one-way command, often 5G being used in order to embed those sensors down into the forest level. So what we'll do is we'll switch our color here, and we will just embed some sensors into the forest environment, realizing that we're using 5G to feed this information back up where the forestry services would be able to monitor and run algorithms to basically keep track of the status and the health of the forest. Okay. We also use sensors in agriculture quite a bit. They do something very similar. They look at health, they look at growth, they look at the nutrition within the soil, the balance of water. They also have the ability to be actuary. And 5G is also used increasingly within agriculture as well. Both of these are very wide geographic technologies, disciplines, forestry and agriculture. So 5G matches these environments fairly well. And from that, we have a feedback up providing an algorithmic space. Now, what are some of the actuary things that we might do in an agriculture environment? Well, obviously, as in times of lack of rain, maybe even drought conditions, we need to irrigate. Irrigation means that we need to pull off of the water distribution network, which means there's an implicit feedback, obviously, not only between agriculture and the environment as a whole, but also between agriculture and the actual water distribution systems. So there's an implicit, we can see that there are a series of implicit interrelationships and feedbacks that are being created in the algorithmic space that gives us a holistic vision of what's going on in the physical space and infrastructure. And this can be very powerful. Other alternatives are pest control, perhaps fertilizing, things of that nature. All of this can be monitored and basically automated by the use of 5G and the Internet of Things. And that's increasingly being done within the agricultural space. Now, let's talk about something that is not as closely related to the environment. The three disciplines that we've been talking about, water, power grids, forestry, and agriculture as one group, these three are highly interactive with the environment. Obviously, that's almost common sense. But when we look at other modes of human systems, they are not as interactive. I don't want to say they have no interaction, but they can exist largely independent outside of extreme weather events such as blizzards and things of that nature. And the first thing we're going to talk about are our traffic systems, our roadways. Now, I love road trips. That's one of my favorite things to do. I love, coming into a metro area. You pass some farms, maybe you'll pass some forested hills. You'll see your cell towers. You come into the metro area, and it gets obviously a little bit more congested. And if you're going, that's your destination. You find your hotel, and maybe you find a nice place to eat and get ready for the next day. On the other hand, if you're traveling through, you will come through, you will grab a major junction, and you'll move off to your eventual destination. And as you move out of the metro area, we go back to forested hills and agriculture. And anyone, I'm sure most of you enjoy road trips as well. It's a very enjoyable experience. But my point here is that there's a lot of IoT on the roadways. Most obviously, our video surveillance. But there's also intelligent traffic management system, the ability to look at the roadway capacity, the ability to monitor and actuate the roadways, particularly in the metro areas during rush hour. So we'll draw another algorithm or algorithmic space to handle our traffic. And we're all very familiar with that, the start and stop pacing when you want to get on the roadway during rush hour, the ability to control lane behaviors as far as directions, how many are northbound, how many are southbound, for example, and that can change dynamically through feedback in this algorithmic space down to actually manage your traffic systems. A cousin to that, very close cousin to that, is transit. Now, this can be either railway transit for cargo, or it can be railway transit for passengers. Both use something called Federal Railway Association Positive Train Control, or PTC. And basically what that comprises, I forgot, we need to draw our sensors for our roadway, and we need to realize that we come in to a metro area, we get high density of sensors, monitoring the traffic, allowing us actuary control. And then again, we get more sparse as we move out into the rural environments. And let's just interconnect this together to give us our representation of our roadway space within the cyber domain. And it's by that we can create this feedback from the roadway systems up into the algorithmic space and then back down, giving us actuary control. Very similar concept here with transit. The only difference being, obviously, is that we're complying to a standard rather than intelligent traffic management systems, ITMS, we're using FRA PTC. And basically what that involves is very similar concept of embedding sensors into the railways for multiple purposes, not only for the state of the track, the switches, but also crossings, locations of trains, and their direction, and basically an overall feedback mechanism of the railway environment, and that is represented by this algorithmic space above. And again, keep in mind that there may be dozens of algorithms running in each of these spaces. And we know that there may be some degree of interaction between traffic and transit as well, being the fact that they are very closely related and they often interact, particularly in metro areas. Now we'll turn to our final subject of public safety. Public safety is embedded everywhere, and we often think of video surveillance systems, but public safety isn't just that. It's also public monitoring, not only for the case of safety to civilians, but also the ability to monitor and provide safety to all of the infrastructure that we're talking about here, and the ability to make sure that it's safe from vandalism or any other events that may occur. But we also realize that this type of visibility and this type of monitoring and public safety can result in increased safety in the roadways themselves for prompt response during times of accidents, things of that nature, for the right emergency teams to be on site to service the community. And again, that has a strong impact to public safety that is outside any aspects of crime or anything of that nature, although obviously public safety is involved very much in supporting and helping reducing crime in many of the metro areas. So that basically shows how a series of relatively low intelligence devices in the physical space level can be interconnected in a neural type of framework, fed up into an algorithmic space where it can be considered, weighted, and then provide actuary control coming back down again from the algorithmic environment down through cyberspace into actuary commands to adjust the physical environment dynamically according to feedback. So now you can see that these small little devices can, at the end of the day, provide a very high degree of intelligence. Thank you very much for your time. I hope you enjoyed this talk as much as I did. Ed Kohler, signing out.